In this video, we will look at expressions of the form a sine x plus b cosine x. Whenever we see things like this that take the form a sine x plus b cosine x, it may be useful to write those two trigonometric functions as a single trigonometric expression using the addition formula for sine. We know this because cosine and sine are very related. The same shape of the curve shifted and translated a little bit, so we can get from one to the other pretty easily. So we'll motivate this and look at a quick example, and then we'll give kind of a formal definition of how to add sines and cosines. So suppose that we want to write 1/2 sine x plus the square root of 3 over 2 cosine x as a single trigonometric expression. So essentially what we're saying we want to do is we want to find some expression that looks like a sine bx plus c. And we want this to be equal to our expression 1/2 sine x plus the square root of 3 over 2 cosine x. If we use the sine addition formula in what we're trying to end up with, the a sine bx plus c, we could say we have a and then sine bx cosine c plus cosine bx sine c. Rearrange a little bit just to make sure that we've got our x's in the places we need them and our constants in the places we need them. We can say a cosine c sine bx plus a sine c cosine bx. And you can kind of see here that now we're trying to draw this connection between this kind of general place, the a sine bx plus c expanded, and what we're trying to write as a single trigonometric expression. So we're trying to get from here to here and here to here. So now we have to figure out what each of the constants a, b, and c stand for. So then we can plug those into the single trigonometric expression a sine bx plus c. So it's pretty easy to see that b must equal 1, right? If we're trying to get from sine bx to sine x and get from cosine bx to cosine x, it's pretty clear that b must equal 1. So we'll just write over here, b equals 1. So what about a cosine c and a sine c? We have to figure out a and c now. So now do you agree that if we take a cosine c, square it, and add that to a sine c quantity squared, these two coefficients must equal these two coefficients, each one squared. And I'll show you why we want to square them. It makes it a little bit easier to find a. So we're doing a cosine c squared plus a sine c squared, and we're saying that equals 1/2 squared plus square root of 3 over 2 squared. So a cosine c squared, that gives us a squared cosine squared c plus a squared sine squared c, and that equals 1/4 plus 3/4, and this equals 1. If we factor out an a squared from the left-hand side, we end up with a squared cosine squared c plus sine squared c equals 1. Now the cosine squared c plus sine squared c, we know what that is. That's just 1. So we end up with a squared equals 1, which implies that a equals plus or minus 1. And we'll choose a to equal the positive solution. So we'll say a equals 1. So a equals 1. So we've got a and b now, so we have to figure out cosine c. So I'll rewrite where we are right now. So we currently have the solution that cosine c sine x plus sine c cosine x equals and we're using this to equal 1/2 sine x plus root 3 over 2 cosine x. Okay, so then the last bit is to say, okay, well, if cosine c equals 1/2 and sine c equals root 3 over 2, if we take inverse cosine of 1/2 and inverse sine of square root of 3, we'll find that c equals pi over 3. So we have a equals 1, b equals 1, and c equals pi over 3. So we can say that 1/2 sine x plus the square root of 3 over 2 cosine x can be rewritten in the form a sine bx plus c as just sine of x plus pi over 3. Since we've got a coefficient there of 1 and a coefficient there of 1 from our a and b, and this is how we can combine the trigonometric expression in the form a sine x plus b cosine x into a single trigonometric expression. Sums of sines and cosines. If a and b are real numbers, then a sine x plus b cosine x equals k sine x plus phi. I use different letters, different variables. It doesn't really matter. Again, I want to remind everybody as frequently as possible that what really matters is the relationship between the variables, what they represent, and how you connect that thing to that thing. So k in this case equals the square root of a squared plus b squared, and phi satisfies cosine phi equals a over the square root of a squared plus b squared, and sine phi equals b over the square root of a squared plus b squared. Now, this is a little bit different than what we talked about, but there are equivalent ways to get the same thing. To arrive at the k sine x plus phi, or the a sine bx plus c, we often won't have a coefficient b in front of the x, but it's important to know that sometimes when you have an instinct on what something looks like, you write it as generally as possible and then fill in the coefficients, fill in the constants based on what you know about the problem. This is a general approach to mathematics, and it's an important skill, important tool to have in your back pocket. And just for the sake of making sure that we're on the same page, that this approach and what I did are in fact the same thing. Remember, so above we were using a squared, and we took the two coefficients and squared them and took the square root, right? So that's how we get k. We kind of use an a squared equals, that was like 1/2 squared plus root 3 over 2 squared, right? That's your Pythagorean identity. So we kind of used Pythagorean theorem above. And then phi we just figured out after we got a, we just took the cosine inverse and sine inverse of what was left.